You should have these notes in your package. And we're looking at reaction kinetics. We're looking at another P diagram. But in this case, we're really looking at geometry. How does geometry affect reaction rate, along with things like energy? And this applies to more complicated molecules that are reacting, where a certain part, if you remember from organic, might be called a functional group, and chemicals have to get together according to those parts of the molecules. So we can see, in order for this reaction to happen, where these things aren't bonded and they have to end up bonded, and these things were bonded and the bond has to break, geometry matters. If this part collided with that end or that middle, or if this end collided with that end or that middle, there's no reaction. These things have to get together properly. But let's say they do. So now we have enough energy. The transition state we know is called an activated complex, and it's going to be very unstable. That's why it's high in potential energy. Not happy the way it is. It wants to change. Things that have high potential energy want to get to low potential energy. So right now this is a very unstable arrangement of atoms. But it turns out, hey, if we can go boom and break that bond, then all of a sudden we end up with these products. Now we see the forward reaction. The activation energy is much smaller than the activation energy for the reverse. So it was 134 versus 360. Because the reverse reaction, we got to measure all the way up. We can see what the delta H is, the minus 226 kilojoules. And we know, since it's negative and also the products have less energy, that it's exothermic. So now we can look at what this reaction is. CO plus NO2 becomes CO2 plus NO. So clearly, what we have here is a carbon atom and a nitrogen atom, and we're transferring an oxygen from the nitrogen to the carbon. But the geometry really matters, and that's what this is trying to show along with the activation energy. Hope that makes sense.